everyone, welcome to Chemistry Under Quarantine. What we're going to do today is basically just continue on with the lecture. If you have any questions or something, you can just send me an email and I'll be happy to get back to you. So last time when we stopped, we were discussing the different reactions that can occur in the interstellar environment. Next on the list is talking about photodissociation. So of course this is when a molecule is hit by a photon and breaks apart into two or more pieces. So we have on the screen here, what looks like a fairly scary looking equation, but really all we're doing is we're taking the cross section, which is a function of energy or frequency, multiplying that by the intensity of the photons as a function of your frequency. And that is going to tell us, essentially, how many photons interact with the molecule. But we're only interested in the photons between the minimum dissociation energy, which is right down here, and then the upper limit is going to be our hydrogen atom photodissociation limit. All right, and this, of course, is because as you get to higher and higher energies, eventually all the hydrogen is going to be ionized. So in other words, above 13.6 eV, all your hydrogens is going to be ionized, and that's going to essentially attenuate that radiation at those frequencies. So we don't have to worry about those high energy photons here. So that's going to basically be our upper limit. And then of course we have to start where the dissociation occurs at minimum energy that we need down here. And the cross section for these allowed transitions is going to be on the order of 0.01 to 0.1 squared angstroms, and it's basically on the same order of magnitude as the surface area of what a molecule would be. As for the photon intensity, since we're only interested in the photons between the minimum dissociation energy and the hydrogen atom photoionization limit, this is going to be in the far ultraviolet, and typically in interstellar space we have around 10 to the 8th far UV photons per square centimeter per second per steradian. And this is assuming that this is going to be in diffuse clouds, so they're not going to be attenuated by dust. On the next slide we'll talk a little bit more what happens when you are attenuated by dust. Typical rates for these work out to be around 10 to the minus 9 to 10 to the minus 10 per second. And if you just take the reciprocal of that, that gives you an idea of the lifetime of molecules in interstellar space. So it's going to be on the order of 1 billion to 10 billion seconds, which is around 30 to 300 years. So, it's fairly long on human time scales, but when we're dealing with millions of years for gas clouds, it can be fairly short. Now, when you're dealing with molecules that are in clouds, the intensity is attenuated by dust, and this essentially goes as Beer's law. So we have here the unattenuated rate, and then we multiply that by e to the minus BAV, where B is basically just a constant for how much the molecules absorb, and then AV over here, this is your visual extinction due to dust. And this is actually related to our color excess, and we covered that way back in the first couple of weeks. So this is essentially just letting us know how much of the light is actually being absorbed inside of the dust cloud here. And it's simply just like 3.2 times whatever our color excess is, so that's the ratio for that. And like I said, A is your unshielded rate. So here are just some typical values for this. And I just want to note one very important thing here on the notation. So you notice here we have a number, and then in parentheses we have another number. And this is just a shorthand notation that is used quite often. Where here like the 2.7 and then in parentheses negative 10, this just means 2.7 times 10 to the minus 10. So that's what that means right there, and that's 1.0 times 10 to the minus 9. So again, it's just a way of different notation just to condense things down a little bit here. So anyway, as you can see, all these are around 10 to the minus 10 to the minus 9. And then you can see your extinction coefficients over here, basically around 1 or 2. In this case over here for carbon monoxide, it's actually a wee bit higher than the other ones, and that's because of the self-shielding is actually important. And we talked about that last time. So like molecules like carbon monoxide, they can go to a excited state, and those excited state transitions occur only at certain frequencies, and then they decay to a low energy state, which then dissociates, or they have some intermediate state that they can then break into. And because of that, carbon monoxide has a lot of self-shielding, unlike a lot of these other molecules. So actually this is why it has a fairly high attenuation coefficient over here for that. All right, now cosmic rays can actually produce ultraviolet radiation inside of dark clouds. So what's happening here is that regular photons are easily attenuated, as you would expect, inside of gas clouds. But the cosmic rays, they have plenty of energy, they can easily penetrate deep into the cloud. But what happens is the cosmic rays, they ionize your atoms or molecules, and then you're going to produce these secondary electrons. And then those electrons have enough energy where they can excite mostly hydrogen, because that's again the molecule that's most prevalent inside these clouds. So those hydrogens are then excited, and then they are going to radiatively decay, and during that time they're going to be producing far ultraviolet photons. And this essentially is going to create light inside of the dark cloud, and then that light can again drive your photodissociation, which can drive your chemical reactions. So here's your photodissociation rate. It's driven here by your cosmic ray ionization rate, which is around 3 times 10 to the minus 16th per second. And then it just depends upon which molecule here, how well they interact with those. So this is going to be your factors over here. And then you have 1 minus the albedo. So the albedo here is essentially like how much of the light is being absorbed by the dust particles. So again, self-shielding for carbon monoxide is actually kind of a limiting factor for a lot of these. But these are just some typical values. But when you run through the numbers on these, we wind up getting about 400 photons per square centimeter per second per steradian. So it's not a lot of light. It's about 5 times 10 to the minus 4 of the unattenuated background if there were no dust there. But if you have nothing, this is still better than nothing and can drive a lot of your chemical reactions in those cases. Okay, the next one we're going to talk about here are your neutral-neutral reactions. So in this case, we have two neutral atoms, or a neutral atom and neutral molecule, something coming along and reacting with one another. So in this case, they're going to be reacting using the van der Waals potential. And this you may recall from the Leonard-Jones 612 potential. Remember, the attractive part goes as 1 over r to the 6th. And right here, here's your 1 over r to the 6th that we're actually talking about. And then we're going to multiply that by your average ionization potential, and then also the polarizability of your species. So in other words, how easy it is for the electron cloud around the molecule to distort. And typically for most small molecules and atoms, we're going to be talking around 10 to the minus 24 per cubic centimeter for that. So this is your typical polarizability for that. Now, as for your forward rate coefficient, it's a little bit difficult to actually derive this whole thing here, but essentially the rate coefficient here goes as the cube root of again your polarizability, your ionization potential, the average, and then you divide that by the reduced mass of the two particles, take the cube root of that, and then you multiply that by the root mean cube of the velocity for this. And typically these forward rate coefficients are around 4 times 10 to the minus 11 cubic centimeters per second for that. And for these reactions, for this rate coefficient over here, this is basically assuming that there is no activation barrier. If there is an activation barrier, then you just have to multiply that by your Boltzmann factor, which is going to be your e to the minus your activation energy divided by kT in those kind of cases. But for most of the time, especially when you're dealing with very low temperatures, if you have any non-zero activation barrier, it's going to prohibit many of the reactions from actually occurring. But if there is no activation barrier, these things will basically collide and then do the reaction in those cases. So here's some typical neutral-neutral reactions. Here's hydrogen plus an oxygen gives you a hydroxyl radical plus hydrogen. That can again react with another hydrogen and then basically just reverse the reaction over here. H2 can react with a hydroxyl to make water and hydrogen. An H plus water can make a hydroxyl radical and hydrogen, and so on and so on. As you can see, typically these reaction rates are on the order of 10 to the minus 9, 10 to the minus 12, somewhere in that vicinity. And most of these have fairly low activation barriers as well for that. So these are all pretty small activation barriers for those things. As for some radical reactions, again, they're also in that same region. Basically, here we have about 10 to the minus 11, 10 to the minus 10 for those values as well. Now, ion-neutral reactions, these are what actually drive many of the chemical reactions in the interstellar medium. These are approximately 100 times faster than the neutral-neutral ones. So even though we saw those neutral-neutral ones that could produce like water and so on, these are actually going to be fairly low on the amounts of chemicals that are actually produced that way. So the difference between ion neutral is that your potential is going to be changing. So now you still have your polarizability. This is just for the neutral atom you're dealing with, or molecule. And then we multiply that by the electron charge squared. And now instead of being a 1 over r to the 6th, this is 1 over r to the 4th potential. So it's not quite as steep as the neutral-neutral reactions. So that means this can basically bring it in a lot easier for those. And when you actually do this, and the derivation is not exactly a trivial thing to do, but we basically get what's known as the Langevin rate. So this right here is 2 pi electron charge times the square root of your polarizability divided by the reduced mass. And these typically are going to be around 2 times 10 to the minus 9 cubic centimeters per second. So this is actually a very typical rate for ion-neutral reactions in the interstellar medium for small atoms and molecules and ions. All right. Now, if you have a permanent dipole on there, this can also enhance your rate by up to like another 100 times. So if you have no permanent dipole, you're not going to have your polarizability is going to be fairly small. But if you have a permanent dipole, you're going to have a much higher polarizability because your molecule already has a natural dipole existing in it, not just an induced dipole for that. So anyway, as for how this actually works, essentially you have your potential here, and if you have some ion going by, it's going to start spiraling in, and you essentially have an impact parameter. So how close does your ion have to be before it essentially spirals in and actually undergoes a reaction? And that's where essentially this this derivation comes from for your rates. Again, it's not a trivial thing to go through and derive there. Right. But the important thing we want to get away from this, because our rate here is so much higher than what we had for the neutral-neutral reactions, small amounts of ionization drive a lot of chemistry. So even though the amount of ionized molecules in the interstellar medium is actually fairly small, that actually does derive most of the chemistry going on there. All right, so here we have some very typical ion-neutral reactions, and you can see these are all around 10 to the minus 9, 10 to the minus 10, somewhere in that vicinity. So the first one is very important here, is the H2 plus the hydrogen molecule makes H3 plus a hydrogen atom. And this is a very, very important reaction. We're going to be actually spending, maybe like a whole lecture just talking more about this molecule. We'll actually do some today here as well. Now, the important reason this is important is as we go down here, you'll notice that H3 plus actually shows up quite a bit. So H3 plus an oxygen can give us our OH plus in a hydrogen molecule. H3 plus in a carbon monoxide can give us protonated carbon monoxide. H3 plus in water can give us hydronium. Then here we have the OH plus and a hydrogen that can make water plus. The water plus and hydrogen can make hydronium. Carbon and the hydroxyl radical can give us carbon monoxide plus. Carbon plus water can give another way of getting the HCO plus. So actually you can see that there's many ways you can actually make certain molecules. So actually you can see right here again, make HCO plus this way, or you can make it this way down here. And you can just basically have to compare the rates. So this is about 1.7 times 10 to the minus 9. This one's 2.7 times 10 to the minus 9. So this way is a little bit faster, but again, it also depends upon what your concentrations are as well. So all these things need to be modeled there. And then here we've got carbon monoxide, in other words H2, again to make the HCO plus. Helium plus, this can react with carbon monoxide, that basically just breaks it apart. Also can react with oxygen to essentially break it apart. Helium and water, essentially that just breaks that apart. And helium and the hydroxide, again, can essentially just break that stuff apart here. So helium ions are actually not seen that often because what's going to happen is you need a lot of high energy to actually form the helium ions, and it's only going to be true very, very close to stars. Meanwhile, the H3 plus, this is going to be very readily formed and is actually going to drive a lot of chemistry over here. So these things down here really aren't too important in the grand scheme of things because they can only form in certain locations, and their abundance is going to be fairly limited. But H3 plus, this is going to form very, very readily and is going to drive a lot of chemical reactions here. All right, now as I was saying, this is going to drive a lot of chemical reactions, and here this is essentially a tree showing a whole bunch of ion-neutral reactions and how we can actually form many common small molecules, basically just starting with a couple of very simple ingredients. So down here we have regular diatomic hydrogen, H2. This gets impacted by a cosmic ray to form H2+, and then that H2+ reacts with another H2 molecule to form H3+. All right, and then this H3 plus is essentially the base of our tree that forms all these other little molecules right around here. So as you can see, it can form with carbon dioxide to make HCO plus, can react with nitrogen to make N2H plus. The nitrogen over here can react with H3 plus to actually form NH2 plus. We'll actually talk a little bit about why it doesn't actually form NH plus in a bit. But then once we have your NH2 plus, it can react with another hydrogen to make NH3 plus, another hydrogen to make ammonium, and then this can react with an electron and basically neutralize itself out to make regular old ammonia. The H3 plus can also react with an oxygen atom to make OH plus, another hydrogen molecule to make H2O plus, another hydrogen molecule to make hydronium, and then that can be neutralized by an electron, and then this can produce water or the hydroxyl radical. H3 plus can also react with a carbon to make CH plus, which will then react with a hydrogen molecule to make CH2 plus. So as you can see, once you have here your CH2 plus, this can react with H2 plus to make methyl cation, and this methyl cation can basically react with a whole bunch of other molecules here to form many simple molecules. So right here, this can react with carbon monoxide to eventually form ketene. CH2CO over here. It can react with water to form protonated methanol, which can neutralize to form regular old methanol. It could react with another methanol to essentially make dimethyl ether, or ethanol, or formaldehyde. These are all possibilities in this case. It can react here with hydrogen cyanide to form your acetyl nitrile. It can react with ammonia to make methylamine down here. It can react with nitrogen to make hydrogen cyanide. And then you could also react with H2 to make CH5+. Now, Now you may say, wait a minute, carbon can't have 5 bonds on it. You know, that's your old Texas carbon. But CH5 plus is actually a stable molecular ion. It's very, very fluxional. It has some interesting properties. We'll talk about those things later. But you know, again, very unstable. So it can react with an electron to neutralize to make rigor-old methane. And then of course, once we have methane, that can start reacting with other methyl radicals. And basically, from this point on, you start just building up all of your hydrocarbons that you actually see there. So all your long chain hydrocarbons that are formed in space can basically form this way. You can start making acetylene or your other simple hydrocarbons. You can make these carbon chains with nitrogens on the end, which are all very, very common. So this is a very, very important tree that actually goes on in chemistry here. All right. Now, hydrogen, the reason this is actually so very, very important is because hydrogen, H2, has a fairly low proton affinity. So this kind of makes it the universal acid. In this case. Now, here we have all of our species over here that we're going to be talking about, and these are ordered in order of increasing proton affinity. Right. Here we also have our ionization energy, the dissociation energy, which counts for molecules over here, and then this would be the Langevin rates for being basically protonated here by the H3 plus. Okay. Now, helium actually has the lowest proton affinity. Okay, so helium hydride ion would actually be, the most acidic thing actually out there. But, forming helium hydride, as we saw, a couple lectures ago, is actually, only formed in certain locations. So it's really not that important of a carrier in the grand scheme of things. So even though this would technically be the strongest acid out there, it's really not very, very important in the grand scheme of things. Here's the hydrogen atom, which again has a proton affinity also very low, and that makes our H2+. And as we saw before, H2+ reacts very readily with another H2 molecule to make the H3+. So this basically lowers this down here because the hydrogen over here has a slightly higher proton affinity. So yes, H2+ would actually be a stronger acid, but it reacts very, very readily with other hydrogen around here to actually make H3+. So that's why we don't count this one. If you notice on the previous slide, we talked over here H3 plus doesn't react with nitrogen to make NH plus. In fact, it just goes to NH2 plus. That's because nitrogen has a very low proton affinity and won't accept a single proton from a hydrogen. So it simply just won't actually accept it because it is more acidic than the hydrogen down here. Oxygen diatomic also has a fairly low proton affinity. In fact, it's really, really close to that of H2. And there's actually been some searches trying to make O2H+, but it's very, very difficult because, especially if you're doing it this way, most of the time, in a plasma, it's just going to react to wound up making water. But you're not going to be able to form, like a stable concentration of like O2H+ that you can study spectroscopically. So it's been very, very difficult to form that, and there's been some calculations trying to see could we actually see this in interstellar space, and the results have basically come up that it's very unlikely that we will to see this in interstellar space. And then finally here we reach H2, and of course this is the very important one that forms the H3+. So this right here is going to be the important acid. Now these could technically be acids as well, but their concentrations in space are going to be much, much lower than regular old H2 down here. So that's why this is going to be like your universal acid. And once you make the H3+ over here, everything below here can be protonated by the H3+. So this really drives our ion neutral reactions, because once you make the H3+, it bumps into something down here. Now these things are charged. Now we can have our ion neutral reactions. Next up are charge transfer reactions. So in this kind of a case, the electron moves between the neutral and an ion. So this is going to be most efficient when your ionization energy is close to the recombination energy of the ion, because in those kind of cases, you're not going to have excess energy that the molecule has to get rid of, or the atom has to get rid of, and that means you're not going to have like extra photons that need to be emitted, which could potentially, while you're waiting for that to emit, wind up dissociating the molecule. So if you just have very close ionization energies between the two species, your electron can essentially move basically like from one desk to another, and there's not going to be much instability in the molecule when you transfer that electron there. So between the proton and the oxygen atom, this is actually a very important reaction, because in this case the proton can basically be neutralized to make the hydrogen atom, and then you make the oxygen ion. And as you look here, the hydrogen ionization energy is 13.598 eV, oxygen's ionization is 13.618 EV. So because these two are very, very close, the electron can essentially just hop from one to the other, and you don't have to worry about breaking up the molecule, or in this case, the atom, and causing additional ionization energy and photons that need to be released. So it's going to be very easy to actually just transfer that electron. It can move very easily between them. And now that you have your O ion plus, your O, the oxygen cation, this can actually participate very, very readily in chemistry and form other molecules. And the rate for this is around 10 to the minus 9 cubic centimeters per second as well. Okay, so next we're going to talk about radiative association reactions. So in this case, two things become one and release a photon. So this can be two neutrals or a ion and a neutral. And what's going to happen here is we have A and B. They react, and they form a unstable intermediate, AB star. And this is going to happen with a rate Ka. And then once this forms AB star, it has two possibilities. It can basically either go back and decay back into A plus B, and then they'll probably just fly away from each other and never encounter each other again. Or AB star can decay radiatively to form a stable compound, AB, and by releasing a photon over here. So what we want to do is figure out, well, what is the rate for that? So here, Ka, this is your association rate. This is typically going to be on the order of the Langevin rate, assuming we're dealing with an ion-neutral reaction, so around 2 times 10 to the minus 9 cubic centimeters per second. Kd is going to be your dissociation rate, and this is going to be around 10 to the 11th per second. So it takes them, quite a bit of time for them to actually come together and react, but once they're up here, it actually can decay fairly readily for this. And then here, Kr, this is the radiative stabilization rate. So in other words, if you're in this way, we either can go back here or forward, and this occurs much less frequently, about 1,000 times per second over here. So very small amounts actually goes this way. Most of it actually just breaks apart for that, typically speaking. All right. Now the radiative lifetime of AB star, again, for typical small molecules, is going to be around 10 to the minus 7 seconds. The collision time scale, so this is the time that A and B are in close enough proximity to one another that they can basically be assumed to form AB star over here, is going to be on the order of 10 to the minus 13 seconds. So if we take the ratio between these two numbers, right, so in other words, they're only in contact for about 10 to the minus 13 seconds, but it's going to take 10 to the minus 7 seconds on average to actually decay. The ratio between these is basically going to give us the percent of the molecules that actually do actually form our stable molecule over here on this side. So the efficiency is basically the ratio of these two numbers. So that's going to basically be your 10 to the minus 10 to the minus 7 divided, 10 to the minus 13 divided by your 10 to the minus 7, which is going to give you 10 to the minus 6 over here. So about 1 in a million is actually going to wind up, giving off a photon over here to form a stable molecule. Right. And the overall rate is actually given by these equations. And actually right now I'm going to go to my other self who will actually show the whole derivation for this. Okay, so I just briefly wanted to show where these rate equations come from. So here I have A plus B is going to our AB star. And this has your forward rate for the association Ka. And then of course there's the dissociation rate Kd. And then once you form your AB star, you could also go by emitting a photon to state AB. That has your irradiative rate of Kr. So for this, the AB star over here is going to essentially be an intermediate, and what we're going to use is a steady state approximation. So we're going to say that over time, the total concentration of AB star is not going to change. So this means that your D of AB star dt is equal to 0. So all this is saying is that the concentration of AB star is not going to change as a function of time. So that's why we call this the steady state approximation. So if that's equal to 0, we can use these relations up here to basically figure out, well, how does this relate to the concentration of A, B, and AB star as well? So if we just look here, that's first of all going to be the concentration of A times B times the rate constant Ka. So Ka times A, B, and then, so that's going to be the amount that this forms, and then we have to subtract off the amount that this decays. So it's going to be minus Kd times the concentration of AB star. And then also, it can only go, break apart into two pieces, or it can go here and, of course, by releasing the photon, go to form AB. So this is going to be, again, minus the Kr times AB star. Okay, and then all we have to do here, we want to figure out what the concentration of my AB star is. So really this is just a little simple algebra. Just bring this over to the other side, and then factor out your AB star, and then divide by Kd and plus Kr. So all we're going to get here is your AB star is equal to Ka times your concentration of A and B all over Kd plus Kr. All right. Now, of course, what we are interested in at the end of the day is, what's the concentration of AB going to be? So, just going to change colors here so we keep our line straight. So the concentration of my AB it's going to be easy to figure this out. All it is, it's just going to be the concentration of AB star times Kr. All right, and since we already know what AB star is from right up here, all we're doing is just taking this equation and multiplying it by Kr. Okay, and if we're interested in our rate, that's everything except the A and B concentrations over here. So therefore, my rate overall is going to be Kr, Ka, all over Kd plus Kr. Now, we can make one simplifying assumption here, is that the rates between Kd and Kr, since we know that Kr here is going to be much, much less than that of Kd, since this is going to be much smaller than the Kd, we can basically just say that the rate over here is going to be approximately Kr, Ka, all over Kd. Okay. And that's essentially how we figure out our rate equation for that one. Okay, so as for understanding some of these numbers, so when they collide, your AB complex is basically going to store the kinetic energy and the interaction energy in the vibrational and rotational mode. So you have your molecule forming there, and it's going to basically start rotating and start vibrating. And while the energy is dispersed evenly between these different modes, your molecule is going to be fairly stable. But eventually, as the vibrational modes are, the energy is being moving between those different modes, eventually it's all going to end up in one mode, and when it all does that, that's when the thing basically breaks apart. So essentially you just have to figure out, as the molecule vibrates, how long does it actually take to, just by chance, for all the energy to basically refocus itself in one mode. So think about, you have a molecule with a bunch of springs and you're shaking it, and the atoms are all bouncing around. Well, eventually, just by random chance, you're going to wind up that all the energy just kind of goes into one of the bonds and is vibrating, and that's going to be enough to break the molecule apart. Right? And it turns out that the lifetime here of the AB star is going to be around 10 to the minus 11 seconds. So that's very, very small. But recall on the previous slide, we said that the collision time is around 10 to the minus 13 seconds. So it's about 100 times longer than the collision time. So when we're saying that AB star, it's not just the time that A and B are in close proximity to one another. There is actually forming like a physical species that is stable, at least for more time than they're just passing by one another there. Okay. Now, if you're dealing with larger species, these are going to have more modes, so therefore your lifetime is going to be much larger. But if you're dealing with, again, fairly small molecules, these rate of dissociation times are going to be, again, on the order of 10 to the minus 11 seconds for that. All right, and if you do have longer times, your rate is going to be higher because you're going to have more time for that energy to dissipate, and then more likely that you're going to give off energy via the photon rather than your molecule prematurely breaking up for that. And here we can actually just see some common small ones here. So here I have a hydrogen and a carbon coming together, and again, these are all very, very small rates. 10 to the minus 17th, 10 to the minus 16th or so. So these are not very, very efficient rates. And notice that for these, we do have like a dipole actually setting up, so that's one way we can get rid of the photon. Remember, like H2, between two hydrogen atoms forming in the gas phase, we can't actually do this because there's no dipole for this to actually, have the to get rid of the excess energy there. Right, and photodissociation is also related to this because essentially it's the reverse reaction for this. So if we just look at this right here, we could very easily just say, well, a photon comes in of the right energy, excites the AB to AB star, and then it can dissociate. So really, this over here could just be very easily reversed if you have photons of the correct energy for that. So next up is a thing called dissociative electron recombination. So we actually saw that a lot on this reaction thing. So you'll notice like the end reactions for a lot of these have an electron right on the end here. And that electron comes in and neutralizes these molecules. And in the case of this, you're basically just also getting rid of an extra proton as well. So, for instance, methanol is stable, But protonated methanol also stable. But if you have methanol with an extra hydrogen atom on it, it's not going to be stable. Same thing like here, hydronium is stable, but H3O neutral, not stable. NH4 neutral, not stable as well. So these electrons come in, they neutralize the ion, and then we form a neutral molecule, and then this usually breaks apart the molecule that was there previously. Now the rate coefficients for these are going to be around 10 to the minus 7 per cubic centimeter, or cubic centimeters per second. So these are going to be fairly fast for that. Now, larger neutral molecules, they can spread the energy over vibrational states, so it may not dissociate, but it depends upon the molecule. So if you're dealing with very, very large molecules, it might not break apart, but most typical small molecules, these will actually dissociate there. Also, very importantly, branching ratios may not be well known. So if you break apart, you don't know if you're breaking apart into, let's say, a water molecule or an H2 and a hydroxyl radical. It's just not known. So it's fairly difficult to find out what these are, because they depend a lot upon the energy, which way the electron perhaps comes in there, where your vibrational levels are and everything. So it really depends upon the individual circumstances, and it's kind of hard to study those things in many cases. All right, and as we're going to be seeing here, your rate and your cross sections can be very, very energy dependent. Okay, so here's some typical reactions. So as we saw a lot of these on that tree before. So over here we have the hydroxyl cation, and again that can just break into an oxygen and hydrogen. Carbon monoxide plus with an electron can break apart into a carbon and oxygen. Water could break into, or the protonate, or the water cation here could break apart into all atoms, or it could break into a hydroxyl radical and a hydrogen, or it could break into an oxygen and a diatomic hydrogen. So these are fairly about the same rate over here. This one actually has a bit of a higher rate, so this one's probably more likely to occur, but again, a lot of it depends upon your energies and stuff. Of course, here's hydronium, so it can basically break apart into a water molecule, or it can break apart into the individual components, in some different ways. This is going to be very, very important for H3 plus an electron to form the H2 and hydrogen. So we're actually going to be talking a little bit more about this one right here, because this is very, very important for our reactions. The protonated carbon monoxide can just break apart into carbon monoxide and hydrogen, and then down here, of course, you have your CH plus, your CH2 plus, and then they can break into some combination of CHs and Hs and everything else coming off of there. All right. Now, for the rest of the day here, we're actually going to be talking about H3 plus dissociative recombination, because this actually has some very important implications for interstellar chemistry, because it's very important to let us know what our expected concentrations are in interstellar space. So when they tried measuring this experimentally over time, so here we have our years, and here is our dissociation rate. You notice that these values differ by quite a bit, so at least over an order of magnitude, and in some cases, 4 orders of magnitude down here. And apparently these were, well done experiments. These were some kooks that did this one down here, but they differed significantly from the rates that were up here. But even so, over time, you'll notice that there's not really any convergence going on, and it depends upon your experimental technique. But there's still a lot of uncertainty in these values in the early 2000s. Also, which didn't help matters, was that in the early 2000s, the theory was kind of in its infancy, so they really didn't understand what was actually going on when an electron hit an H3+. We do now know better, but at least back then it was kind of difficult to actually know that stuff. So the main problem with all these experiments was actually recording H3+ in the ground state. So when you're dealing with H3+ and you're forming it, it has to basically form in the laboratory under fairly violent circumstances. You need a plasma, which is going to be usually fairly hot, and you are starting with hydrogen, which is going to be at room temperature. And when that happens, your H3+ is going to be formed in vibrationally excited states and rotationally excited states. That is going to be different than the H3+ that is actually in space, which is going to be very, very vibrationally and rotationally cool. So there needs to be a way to cool down the H3+ molecules, which is not a trivial thing to actually accomplish here. But the experiment that they did was actually using Cryring, which is a ion storage ring in Stockholm. So essentially you'd form your H3+ out here. It goes through some tubes over here basically to get all the right energies and everything. And then it's injected into a storage ring and goes round and round and round. And of course you have your magnets and things to basically keep these things, the correct energy and stuff. And then we have over here is an electron cooler. And then what's going to happen is you have your electrons basically added to the system over here. And the electrons are going to interact with the H3+ in this region, and then they're going to break apart. And then you can just record, how much of them break apart as a function of energy between those two. Okay. Now, as your H3 plus is stored in this ring, it can vibrationally relax. So, it can be stored in there for, hours. As long as you want to, basically, it will stay very stable inside of there. The molecules, on the other hand, are still going to be very rotationally hot. The rotationally cool time for H3 plus is very slow, at least, for reasonable human time scales here. So it's going to be very difficult for that to actually happen. H3 plus doesn't have like a permanent dipole moment, so it can't give off its energy rotationally and cool down that way. And in other words, there's no rotational cooling while it's actually going around the ring. So vibrational will cool down. So you'll be in the lowest vibrational state, but it'll still be at a high rotational state. But what you can do here is control the H3 plus electron impact energy. So in this little region, which is right down here, the H3 plus is traveling along, and then you have your electron beam, and then you can tune the energy of that electron beam, and you'll make it either go a little bit faster or a little bit slower than the H3 plus. And by tuning that, you can see how much decay products, your hydrogen or diatomic hydrogen, come through and hit the detector. So essentially, you go there, tune your energy of your electron beam, and say, oh, I got more coming at this energy, less coming at that other energy, and then you can make a nice little plot of those things. But still, we had this problem that there was no rotational cooling. So how can we actually wind up solving that? Well, what you need is a supersonic jet. So up here, we have high pressure hydrogen, about 2 atmospheres, and this goes through a solenoid valve. And this solenoid valve over here basically gives a little pulse, so it moves up, and then there's a 900 volt ring electrode here, so basically a little spark gap, and then that's going to ionize the hydrogen to make your H3 plus. We have some skimmers out here basically to make sure that the pressure doesn't get too much in the ring. You always want these things at very, very low pressures, on the order of microtorr, and you just let only small amounts of the H3 plus go through. And when you do this, you wind up with a pulse of rotationally cold ions. Okay. So you can actually characterize this. So here's an absorption of H3 plus. We'll actually talk probably next time more about the what these energy levels actually are here for the H3 plus here. But these are very, very rotationally cold. They agree with like the absorption seen in Xena Percy, which is a star. We'll talk about that in a bit here. But these are very, very rotationally cold, as you can also see by the width of these lines. So that means that there's not a lot of Doppler broadening going on for these as well. All right, so how does a supersonic jet cool things? All right. So what's happening is we first of all need a huge pressure drop. Remember, we started at 2 atmospheres over here, and then down at this part in the system, we're down to microtorr. So inside the high pressure, the gas is basically bouncing around in here all randomly. But to escape this little pinhole through the little solenoid, the gas has to be going only in a certain direction. So that basically selects. Any gas molecules going the wrong way obviously won't go through the hole. So only gas molecules going the right way are going to go through the hole here. So basically they're all rushing out. Just like water through a hose is all going basically in the same direction. Right? Now in this region here, since there's not other gas molecules around, they're not going to start bouncing randomly. They're basically just going to continue on going in their same direction. So there's only going to be like a few collisions going on in this region here, and that's going to basically help cool things down by quite a bit. So as we look at this, in here in my high pressure, you can see on the blue curve, this is going to be basically the gas at 300 Kelvin. So that's your normal Maxwell-Boltzmann distribution. But then the gas coming out of here, all that random energy has basically moved the speeds here to a very narrow velocity distribution, because they're all now going basically in the same direction here, because they're all going that way. But their width of their speeds is going to be much, much reduced. So essentially they're all going at, let's say, 2,000 meters per second here, but the spread is much cooler. So yeah, they're all going very, very fast. There's a gigantic wind going this way, but as you look this way, they're actually very rotationally cold going like that. So for this to happen, your velocity deflection, you need 1 collision. Translationally cool, so these are going to make these very translationally cool this way. That only takes about 10 collisions, so that's can easily happen inside this thing as it's expanding here. Rotationally cooling takes about another 100 collisions for this to actually happen. Now to vibrationally cool things would need about 1 million collisions, but actually in this whole nozzle expansion here, we're actually only dealing with about 1,000 collisions. So there's not actually enough time to vibrationally cool the molecules, but there is plenty of time to rotationally cool them and translationally cool them. But fortunately, as the H3 plus is going around the ring, it's able to vibrationally cool. So all you have to do is put it in the ring, wait a little bit, and your molecules will be vibrationally cool, rotationally cool, and translationally cool. And then you can do your experiment on them and find out what the cross-section is with respect to energy there. Okay. So like I said, they make it rotationally cool there, but not enough to vibrationally cool all of them here. Okay, so here's the results for this. So as we see here, we got actually a very, very interesting pattern. And you notice there's like a lot of little wiggles kind of going on here. These are actually real resonances going on here. This is not just noise because it is reproducible. And there's actually another ring that they're doing this, I believe, in Germany, and they got essentially the same results. All little bumps and wiggles lined up perfectly there. So this is a real result, and they've very confident in that. So essentially, here's your reaction rate between the electrons and the H3 plus. This is your detuning energy. So essentially, what was the energy of the electron versus what was the energy of the H3 plus going by there. So as you can see, if they were very close in energy, you had a very high cross section around 10 to the minus 6. If they were around 1 eV difference, they were fairly low in energy for that. So how do we use this information here to basically figure out, well, what is our rate coefficient generally going to be? Well, this is how the cross-section varies as a function of energy. And then if you know what the temperature of the gas is, you can figure out, well, what is your actual Boltzmann distribution of your electron energies in there, and essentially just have to multiply the two together, integrate, and you get essentially this curve, which gives you what is going to be the rate coefficient as a function of temperature. So here this is like 23 Kelvin, which is going to be typical in like a diffuse cloud, and then 300 Kelvin would be like like at room temperature here. But as you can see, that's why there was a lot of variation between these experiments, because maybe some of them were more cool than others, some of them were a little bit hotter than others. So that these down here were probably a little bit hotter temperatures, and these down here were probably a little bit more on the cool side. So yeah, I mean, some of these values did kind of agree-ish with the expected values, but now at least there's a definitive cross-section understanding of the H3 plus with electrons actually going on there. Okay. So why do we go through this entire thing here? Well, first of all, when they were actually doing their telescope time, what they realized was they found H3 plus, but there was way, way, way too much in diffuse clouds. So right here we have a spectra of some H3 plus, and this is towards Cygnus OB212, which is a B-class hypergiant. It's actually one of the most luminous stars in the galaxy, about 1750 parsecs in distance away from us. All right. Now the whole big paradox here is that H3 plus has been seen for a long time in dense clouds, and it's expected to be there. They found it fairly easily. But the column density in these diffuse clouds was essentially the same as what they were seeing in the dense clouds, which didn't make a lick of sense because diffuse clouds have a lot less hydrogen, so they should also have a lot less H3 plus. In fact, it should be basically impossible to actually see that. But they were seeing H3 plus essentially as abundant as it is in dense clouds. So this was a bit of a conundrum here. All right, now the chemical model had the concentration of H3 plus at around 10 to the minus 7 per cubic centimeter. So here we have essentially our column density, which says how much H3 plus is between us and the star. Here we had the chemical model, which basically says how much H3 plus there should exist there. So if you divide these two numbers, you'll basically get a length. And this length here works out to around 10 to the 21st centimeters, which is about 1 kiloparsec, which is on that same order of magnitude as the distance away, but really doesn't make much sense because that would basically imply like the entire galaxy, if this like half this distance here is basically filled with H3 plus. So that would basically imply like most of the galaxy is filled with H3 plus, which doesn't make a lot of sense on the face of it. So there has to be something else going on here. So what we have to do is look at our diffuse clouds and the other diffuse clouds where this was actually seen, and the reactions that are actually going on in these cases. So I'm going to go to other me, and we're going to show you the derivation for these diffuse clouds and show you where these where the reaction rate actually comes from here. So this is basically the concentration of the H3 plus, and I'm going to pause right here and basically just show you how this is actually derived. Okay, so I want to show you briefly where we get that equation for the concentration of H3 plus, just knowing the cosmic ray ionization rate, the dissociative electron recombination rate, and the H2 and electron concentrations here. So, of course, what goes on here is we have a cosmic ray impacting a hydrogen molecule, and this has, the particular rates, and I'm never very good at this particular Greek letter here, or zeta, gives us our cosmic ray plus H2 plus an electron. So over here, the cosmic ray, unlike other reactions where it when it comes in stops after it reacts, this is kind of like a toddler in a store. It basically just keeps going and wreaking destruction wherever it goes. So this cosmic ray, the concentration of this really doesn't matter. It's simply just the rate. So really, we could view this simply as the hydrogen here is breaking apart into H2 plus and an electron with the particular ionization rate that we actually do have there. Okay. So then we have this first equation, and then once we form our H2 plus, the H2 plus here is going to react with another hydrogen molecule and form our H3 plus, and a hydrogen atom will come off of that. And this is going to have a rate, I'm just going to call that K1 there. And then this is how we form the H3 plus, and of course we have to have the destruction of this. So here the H3 plus is going to react with an electron to form our H2 and hydrogen, or it could also just do 3 hydrogens. Either way, it doesn't really matter, but this has that rate Ke. So again, we're going to use these equations here to figure out what is my concentration of the H3 plus, and we're going to again use the steady state approximation here. So we're going to say that the concentration of H3 plus with respect to time is equal to 0. Or I should say the change in H3 plus concentration with respect to time is equal to 0. With this right here, because this is where we haven't formed H3 plus yet, so right here, this is where we're forming it. So we're looking here at the concentration of, using our K1, times the H2 plus, times the H2 concentration, and then we're going to go and subtract off, dissociative recombination. So this is going to be minus the Ke times the H3 plus concentration times the electron concentration. Okay. So we want to figure out the H3 plus concentration. It's just a little simple algebra. Just have to move things to the other side and divide. So we wind up here getting my H3 plus as equal to what I'm going to call my K1 times the H2 plus times the H2. Divide that by my Ke, and then multiply that by the electron concentration. Okay, so we're not quite done. We have to just get rid of the H2 plus concentration, and there we're going to use our steady state approximation once again. So just a different color here. So d H2 plus dt is equal to 0. And if we look at this, we form this over here using my cosmic ray ionization rate. So now here's my cosmic ray rate times the H2, and then it's destroyed over here using the K1. Okay, so minus the K1 times the H2 plus times H2. And at this point, we just want to solve for what my H2 plus concentration is. So again, just a little simple algebra here. So that's just going to be the ionization rates times the H2, and then divide that by the K1 times also the H2. So if we look at this, you can see that the concentration of H2 plus is basically independent of the H2 concentration. So actually these just cancel each other out, and it's just going to be simply the rate, or the cosmic ray ionization rate over here, divided by the K1. So we can just plug that in to this equation that we have up there, and we see here, I can just write this right next to it, for my H2, notice this is going to be my, I'm going to write this. So here's my K1, and then times the H2 concentration, divide that by my Ke and the electron concentration, and then we just have to multiply that by these values down here. So my cosmic ray ionization rate divided by my K1. So as you can notice, K1s go away. So what we're left with here is the final answer. This is going to be my rate, my cosmic ray ionization rate, times the H2 divided by the Ke and the concentration of your electrons. And that's going to be our final answer here for what the concentration of H3 plus is and how we get that. So, as I was saying here, the formation deals with the cosmic rays bumping into hydrogen, ionizing to make the H2 plus. And then that H2 plus reacts with the H2 and of course make the H3 plus, and then it can be destroyed via an electron. Now, from this, we can see that we have our cosmic ionization rate, or cosmic ray ionization rate, the ratio between hydrogen and electrons, and then also the electron dissociation rate, all right, or the electron recombination rate here. Now this one, we've just experimentally established what we know what that value should be, so this is fairly good. And then we're going to look at these other two quantities, the ratio between hydrogen and electrons, and then also the cosmic ray ionization rate. All right, so here, this was basically a lot of the other stars and stuff, and also, like I was saying, they were seeing the H3 plus column densities. These are all diffuse clouds, also be very, very important as well. Okay, so this was the experiment that they did. They looked toward Xena Percy, which is a B-class supergiant 230 parsecs away in the constellation of Perseus. Has a visual magnitude of 2.9, so if it's not cloudy outside, you can actually go and see that. So actually right here, that's what Xena Percy is, right, if you're looking for it. So over here, this was the H3 plus concentration. So again, remember what's going on here is we have a star over here, and then it passes through some diffuse cloud over on this side, and then of course over here on Earth, we're actually observing it. So these things that we see in a star are not actually from the star themselves; they're actually from the intervening gas over there. All right. Now, what has been done previously, they found the concentration of hydrogen. This was using the ultraviolet stuff from Copernicus, and they knew what the concentration of the hydrogen was over here. And the Hubble Space Telescope over here gives us our concentration of our carbon. All right, and the ionized carbon here is actually going to be the primary source of electrons. Because remember, photons with energies greater than 13.6 eV, the ionization of hydrogen, are going to be severely attenuated. So really, that means by the time the hydrogen or the photons get into the diffuse cloud, all that's been attenuated. So basically, you have the photons between your 11.2, which is the ionization of carbon, to 13.6, and that means that only the photons that have enough energy to ionize carbon are going to be ionizing carbon. So if you see how much ionized carbon you have, that's going to give you an idea how many electrons you actually have there. So from this result here, we actually have a very good idea what the amount of electrons in this region actually is, and it's directly related to the amount of ionized carbon in there. So remember, this is the ionized carbon. This is one of those semi-forbidden transitions here. All right, and essentially when you run through these numbers, this kind of rules out the hydrogen to electron ratio, because this is going to be very well known. It's fairly well established. So now we can start looking at some of those other things as well. All right. So here is that, the concentration of H3 plus equation that we just derived. So over here, we have, just by rearranging this, because this concentration is just going to essentially be your number density divided by the length here. Just by rearranging this equation, we can see that the cosmic ray ionization rate times the length between us and the star here. That's equal to our electron dissociation rate, your concentration of the amount of H3 plus that we've recovered, and then your ratio between the electrons and the hydrogen. So we plug in these numbers. So this value here, we got that experimentally. This value we measure from spectroscopy from the line. And then this value over here we got from those other two spectroscopic techniques. So all these things are very well known. And when you multiply that out, you get a fairly reasonable 8,000 centimeters per second. Now, this is a velocity, but it's just because, again, we're dealing with, this rate here, which is 1 over seconds, and then this length, which is going to be in, a distance. So even though this represents a velocity, don't think of it as a velocity. It's just that the units happen to work out that way. So there's a couple of ways we can go and talk about this. We can basically say, well, let's use the known ionization rate for a typical dense cloud that was known at least at the time. And for this typical dense cloud rate, this means that the length of the cloud has to be around 85 parsecs, and your number density is going to be around 6 per cubic centimeter. And both these numbers really don't make a lick of sense in the grand scheme of things from what we know from other data that we've actually gathered. So this basically gives us lengths which are way, way, way too big, so really don't make too much sense in these kind of cases here. On the other sense, let's try saying a reasonable cloud distance, about 2 parsecs or so. And when you plug that kind of thing in there, we get a new cosmic ray ionization rate, which is around 1.2 times 10 to the minus 15th, which is about 40 times higher than this value over here. But it's basically, they've actually looked at other sources as well. And, this basically all kind of agree that perhaps what's actually going on here is that the cosmic ray ionization rate is higher than, what we were previously estimating, at least in these diffuse clouds here. Okay, so the whole conclusions that we basically were able to derive from this chemistry here is that for some reason the cosmic ray flux is enhanced over what we actually see in the dense clouds. Now, perhaps the low energy cosmic rays are more abundant. Maybe it's that they're being deflected by magnetic fields, or they're colliding with more particles and losing more and more energy. So perhaps the low energy cosmic rays are going to be more abundant in diffuse clouds than they are in other clouds. So it's maybe that the dense clouds attenuate them more than they thought. So these are some possibilities, but it's been fairly conclusively shown that cosmic rays are not quite as easy to measure, especially when you don't have a detector actually sitting out there and measuring these things. So it's actually opened up a whole host of new things to talk about as to the chemistry that's actually going on in these very, very diffuse clouds here. Okay, so I will stop that here, and we'll pick up with this stuff next week. All right, everyone, stay healthy, wash your hands, and you will hear me then.